Here we have an example of two children playing on a seesaw. So not quite a biomechanical system, but a system that we're all familiar with, or at least most of us will be familiar with this system. Now, quite early on as a child, you would have worked out who you would have preferred playing on the seesaw with. Someone who was heavier than you meant you were stuck in the air. Someone who was lighter than you meant that you were slammed into the ground. So you quickly worked out who was the better partner on the seesaw. And this is really just a consequence of your respective weights creating a moment and how these moments combine to turn the system. So we're going to have a look at an example here. So in this example we have two girls playing on a seesaw. So before I start anything, I usually like to have a diagram. And I'm going to assume that the seesaw is horizontal because it makes our maths easier. Okay, so on our left we have Mary, and on our right we have Rose. The question says that Mary has a weight of 300 newtons and Rose has a weight of 250 newtons. And we're told that each girl sits 1.5 meters away from the axis of rotation, or fulcrum in this case. Alright, so the question asks us which of these two will be stuck in the air. And you can probably look at it now and tell me, but we're going to do the mathematics behind it. So basically, when we're looking at which girl will be stuck in the air, what we want to know is what's the overall moment of the system, or the net moment. So the question's asking us, what's the net moment of the system? So to answer this, I'm actually going to follow the procedure that I outlined in the previous chapter. So that says that, number one, we need to identify the axis of rotation. That's the first thing we do before we start anything else, and this is usually the easiest bit. So in this case, the seesaw is rotating around its fulcrum, and so its axis of rotation is what I've highlighted in green here. I'm writing in blue at the moment, aren't we? Okay, done. Number two, it says identify and quantify all eccentric forces. So for an example on how to, let me move that up, that box hasn't disappeared about the microphone. So we learned how to identify eccentric forces in the first example. So if this is unfamiliar, I suggest you run through that example quickly before proceeding here with example 2. So just to run through it again, identify eccentric forces. Remember, we just need to extend each force's line of action, and if it never runs through the axis of rotation, it's eccentric. So as you can see, the grey dashed line will never run through the green blob, and so we have an eccentric force here with Rose, and following the same logic we can show that Mary also has a line of action that will never intersect with the green blob, and so it too is eccentric. So we've identified which forces are eccentric, and then the second part of part 2 says quantify them. Now some questions are a little bit irritating in that they're not given in the right units, so they might have been given in kilograms, for example, and you'll have to change them around. But here the forces are already given in newtons, so there's nothing further we need to do. So part 2 is now complete. So we can move on to part 3, which is identify and quantify all moment arms. So remember, the definition of moment arm is the perpendicular distance from the line of action of the force to the axis of rotation. So if we have a force in the vertical and a distance in the horizontal, we actually already have a moment arm because they're already at right angles to one another. And that's the case in this system here, where if we have a look, our forces are in the vertical because they're weight forces, they always point down, and our distance is in the horizontal. So here we already have them at right angles. Okay, now remember, to determine moment arm is really dependent on the scenario you're examining. So it happens in this case, but it may not happen in every case. So we're going to have a look at different examples when these don't happen to be at right angles to each other. But fortunately for us, we've already done that. Well, we haven't done it. The question has been presented in such a way that the moment arm is the distance. And so the moment arm of each force is 1.5 meters. So that's part 3 in the procedure complete. Part 4 is to determine the direction of rotation. That each eccentric force creates. Alright. Now, the sticking point here is a lot of people think a downward force is always associated with a clockwise moment because downwards is negative y and clockwise is negative. Don't make that mistake. It really depends on the situation. So if we have a look at it, on the left-hand side, the force is pulling downwards, okay, which means that the seesaw is likely to rotate anti-clockwise. Okay, so that's the direction. Yeah, it's going to pull downwards. And the downwards pulling relative to the axis of rotation means that it's going to create an anti-clockwise moment. Okay. In contrast, Rose's weight is still pulling downwards. Okay, but it's pulling downwards on the other side of the fulcrum. So it's going to want the seesaw to rotate. Let's try that sentence again. It's going to make the seesaw want to rotate clockwise. So both forces are pulling downwards, but because they're on opposite sides of the fulcrum, they're going to create a moment in opposite directions. So really take into account each situation individually. Don't blanket memorize these. Okay, so that's part 4 done. Part 5 is to apply the moment equation. To each eccentric force. Okay. So, remember, moment is simply plus or minus, which the maths won't tell you. You have to work that out. The force times its moment arm. Okay, and I might put a P there for perpendicular, just to remind you. So, the moment that Mary's weight creates is positive because it's pulling in an anti-clockwise direction. Her force is her weight of 300, and her moment arm, which is the perpendicular distance from the axis of rotation to the line of action of force, is 1.5. So Mary creates a moment that has a magnitude of 450 Newton meters. Repeating the process for Rose, I'm going to go over the page. We've got moment due to Rose is negative because she's pulling the seesaw in a clockwise direction. Her force is 250, and her moment arm is also 1.5. And so that comes out to be minus 375 Newton meters. Alright, and now we're nearly finished. So part 6 says sum the moments. in part 5. Sorry, I'm not sure why I dotted a P, that's bizarre. Sum of the moments that you calculated in part 5. So that simply means what we're going to do is the net moment, M net, is the moment due to Mary plus the moment due to Rose. And that would extend across regardless of how many, depending on how many eccentric forces we have. But in this case, we've only got 2, so we only need to sum up 2 numbers. So we've got 450 plus minus 375. Okay, so we end up with the system having a positive 75 Newton meter moment. So that means that it has a magnitude of 75, and because it's positive, it means that the whole system wants to rotate anti-clockwise. So the child that will be left up in the air is Rose. So therefore, wow, I'm really sorry guys, geez, in the air, so in the right area for some reason. Okay. As I get a bit of an addition to this, I won't do it for you, but we can discuss it in your laboratory classes if you want to. Where should Mary sit? If the net moment of the system, so if the net moment is to be 0. And I'll leave that one for you to answer.